All right, so welcome to this week's weekly review. Today we're going to be covering sections 2.8, which are going to be derivatives of functions, and section 3.1, which is going to be derivatives of polynomials and exponentials. So now let's go ahead and get started with derivatives of a function. So last week we explored taking the derivative of a point. And when we took the derivative of a point, we went and defined it as the derivative at a certain point A, or f prime of A, equaled the limit as h approaches 0 of f of A plus h minus f of A all over h. So hypothetically, we could plug in any value we want for A, and we can get some number out and tells us what the derivative of the function is at that point. It'll give us some sort of number. But we can go ahead and expand on that. What we can do is we can actually, since this is typically valid for any point A that we choose on a function, then we can actually go ahead and make this more generalized. So what we can do is we can actually go ahead and just say, how about for any x, we can plug this in. We can, so the limit definition of a function is going to be, we can get a general derivative of a function in terms of x, or f prime of x, equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So once again, this is just pretty much what we did last week, but now we're getting a generalized function that can be applicable for pretty much any value of x. So we can go ahead and just solve for a general derivative of a function, and then we can just plug in whatever points we want after that. So let's think about derivatives. So let's think about what derivatives of functions are. So last week we said that derivatives are essentially rates of change. So we can actually go ahead and look at this and apply this to general examples. So let's say we have the function f of x equals x cubed. If we draw our graph like this, it's going to look something like this. Now let's think about the derivative of our function. So the derivative of x cubed is going to be 3x squared. And now let's go ahead and look at the graph for that. Three x squared is going to end up looking is going to be an upwards facing parabola. So now let's go ahead and look and see if we can find anything in, or see how this leads into one, and see how our derivatives are going to be of a function are going to be related. So like we said last week, if we can take the derivative of a function at a point, we can find its slope at that point. So for example, we can see right here that on our original function, the tangent line at x equals 0 is going to have a slope of 0. Well, if we apply this to our derivative function, we can see that our derivative touches at one point x equals 0. And let's also think about the way our functions are set up. As our cubic function ends up getting bigger and bigger and bigger, its slope starts getting steeper and steeper. And we can see our slope is going like this to this and getting steeper and steeper. And we can see the same thing happening as we keep going up our parabolic function, which is our derivative. So this kind of shows how we can kind of just apply this at any point, and then how we can just kind of apply our limit definition and see how we can actually go ahead and apply our limit definition to a more generalized function and see how that's always going to apply for any x value. So now let's go ahead and try a couple of examples of trying to find just some basic limits. So what we're going to do, so the first example I want to try is we're going to find the derivative of f of x equals x squared plus 2. So now let's think about our basic definition, which is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So now let's go ahead and get started. So let's go ahead and start setting up our limit. So we have our limit as h approaches 0. So now instead of plugging in just a normal value, we're just going to leave x and h just as they are. So what we can do is, so we have our f of x plus h is going to end up being x plus h squared plus 2 to our f of x plus h minus our initial function, which is just f of x, which is equal to x squared plus 2 all over h. So now let's go ahead and factor this out and see if we can do anything more with this. So now we're going to get our limit as h approaches 0. And now we have x squared plus 2xh plus h squared plus 2 minus x squared plus 2 all over h. All right, so now let's go ahead and see if we have any terms that can factor out. So far we can go ahead and get rid of these two x squareds as well as the two 2's. And now this leaves us with the limit as h approaches 0 of 2xh plus h squared all over h. Well, there's a common factor of h in the numerator, and we also have an h in the denominator, so let's go ahead and we can go ahead and eliminate those. H, and then one of these h's. Now this leaves us with our limit as h approaches 0 of 2x plus h. But if we have h approaches 0, we can essentially just eliminate that and essentially say that's essentially equal to 2x plus 0, which would give us 2x. Therefore, the derivative of our function, f prime of x, is going to equal 2x. So now let's go ahead and try this out and see if, just kind of give this a look and see at different points and see how these compare. So if we have our f of x equals x squared plus 2, and our f prime of x equals 2x. So now let's just try to look at a couple different points and see how these line up. So let's go ahead and let's go ahead and split this screen so we can go ahead and draw our graphs. So our f prime of x is just going to be a linear function. And then we're going to have our x squared plus 2 is a parabola. All right, so now our parabola is going to look something like this. So now let's say we want to find the slope of the tangent line at x equals 0 and plus and minus 1. So now what we can do is we can go ahead and just plug in our x values into our derivative to find the slope of the tangent line. This kind of makes things a little easier if you want to look at different points rather than having to plug each one separately into our original definition. So if we go ahead and we take f prime of 0, we can get 0. It's going to be 2 times 0, which is just 0. If we take f prime 1, we're going to get 2 times 1, which is just 2. And then let's do our f prime of negative 1, which is just going to be negative 2. So now let's go ahead and look and see how this compares to our graph. So let's go ahead and star this in green, star this one in orange, and we'll star that last one in purple, just so we can get a better picture. So let's go ahead and look first at our tangent line at 0. So if we go ahead and draw that out, we can see it's going to just be, that looks right, it's just going to be a horizontal tangent line. And we can also see that right here it hits at y equals 0. So now let's try looking at our point at x equals 1. We can see right here that it has a little positive slope right here. It's going up a little bit. It's not super steep, not super shallow. That fits pretty well with our f prime of 1 equaling 2. Now let's go ahead and look at f prime of our negative 1. You can see once again it's a similar slope, just not super steep, not super shallow. We can also see that it's pretty much the same like scale, just with a different sign as our other one. So that makes sense that we'd go ahead and get the same slopes just with different signs at 1 and negative 1. So we can, like I said, so now we can go ahead and see how this can all relate exactly, how our initial function, our derivatives can be related even on a general level. So now let's go ahead and try another derivative problem. This time, we're going to go ahead and we're going to take the derivative. We want to find f prime of x when we're given f of x equals the square root of x minus 1. So as always, we can just go ahead and plug this straight into our derivative, into our limit formula. So let's go ahead and we can take our limit as h approaches 0 of, we're going to go ahead and have 1 square root of x plus h minus 1 minus the square root of our initial function f of x, which is going to be x square root of x minus 1 all over h. So we can't really do a lot with this right now, but what we can do is let's go ahead and just try getting rid of these radicals in the numerator. So let's go ahead and try taking the conjugate, which is going to be multiplying times square root of x plus h minus 1 plus the square root of x minus 1 on both the numerator and the denominator. All right, so now let's go ahead and multiply this out, and we are left with getting our limit as h approaches 0, and we can see that these radicals are going to cancel out. So we're going to be left with x plus h minus 1. The middle terms are going to cancel out, and we're going to be left with a minus x minus 1 all over h times square root of x plus h minus 1 plus the square root of x minus 1. All right, so let's look and see if we can simplify this any further. So what we can see is we can actually go ahead and distribute this negative, so we get a plus, minus, plus, and then we can see that these x's are going to cancel out, and these ones are going to cancel out. So now we're going to go ahead and get back to the form, and now we're going to go ahead and take this, and we're going to be left with having just an h in the numerator, and then we're going to have our h in the denominator times our square root functions. Well, these h's can go ahead and cancel out as well. So now we're down with just having just a 1 over the square root x plus h minus 1 plus square root of x minus 1. Well, these h, since we're taking the limit as h approaches 0, we can essentially just, once again, just kind of treat that as a plus 0 in this root down here, to where this is going to bring us over to having 1 plus the square root of x plus 0 minus 1 plus the square root of x minus 1, which will bring us to 1 over square root of x minus 1 plus the square root of x minus 1. And we can simplify that a little bit further, leaving us with our final derivative of our function as being 1 over 2 times the square root of x minus 1. But now if we look at this, there's something kind of interesting here. In our initial function, f of x, our domain is going to be x is greater than or equal to 1. Now, if we go ahead and look at our derivative, we can't have 0 in the denominator. So we're going to have a similar domain where x is going to be greater than 1. But it's interesting to note that if we have our derivatives and they have limited domains, actually they're going to be very similar, if not the exact same domain in the derivative. So now let's go ahead and try one more example that also has a limited domain and see if the same thing works out. This time, let's go ahead and we can define our function as being f of x equals 1 over x, and we're wanting to find f prime of x. So once again, let's go ahead and just start plugging straight into our formula. So we're going to have our limit as h approaches 0, and we're going to get 1 over x plus h minus 1 over x all over h. So now we're kind of stuck. There's not much we can do right now, but let's go ahead and try doing a common denominator in order to see if we can move anyplace else with this. So, which is going to end up giving us the form of x over x squared plus hx minus x plus h over x squared plus hx all over h. So what we can do is we can actually go ahead and combine this one more time and give us x minus x plus h all over x squared plus hx all over h. So now let's look at this. We can go ahead and actually cancel out those two x's right there. Oh, let's go ahead and fix that sign. That's a minus right there, kids. Always check your signs. So now let's go ahead and move. So now let's go ahead and see what we're left with now. We are now left with having a negative h over x squared plus hx over h. Now, right now we kind of have this weird double fraction. So what we can actually do is, since really what we're doing is we're dividing h, that negative h, by x squared plus hx. We're dividing that by that. Then we're going to divide it one more time by h. So, but then when it makes sense, if we can just go ahead and move this down here all the way to the bottom. Since essentially we're dividing negative h by both terms, so we can actually go ahead and combine them and just say that we're doing it all in one step. So that's going to get us to the limit as h approaches 0 of negative h over h times x squared plus hx. All right, so now you can finally move somewhere again. So we can go ahead and eliminate these h's. So we're just going to be left with a negative 1. So now we can finally take our limit. So we can now take our limit as h approaches 0 of negative 1 over x squared plus hx, which is going to which is going to pretty much approximate out to -1 over x squared times 0x, which is going to be -1 over x squared. So therefore, our f prime is going to be our -1 over x squared. All right, so let's go ahead and look again and see if kind of that similar idea we had still stands. So our original domain is just x is not equal to 0. Now let's look at our derivatives domain. And this time, we still get x does not equal 0. So now this leads us to be able to define if f is differentiable at a point A. So we can say if function f is differentiable at x equals A if if the derivative exists. Then we can expand that a little bit further and say it is differentiable on an open interval from x equals A to x equals B if it is differentiable on that interval. So this is just essentially explaining so essentially it's breaking this down as saying, does the derivative exist if we can take the derivative? It's pretty intuitive. It's just a longer way of saying we can take the derivative, it's just a longer way of saying, okay, how do we know for sure that this is differentiable? Well, we can take the derivative. So now this leads us to thinking about, well, how do we know when a point or a function is differentiable? This brings us up to another theorem. If our function f is differentiable at x equals A, then it must be continuous at x equals A. So now let's think about this. So we have this theorem saying that our function is differentiable if so essentially what it's saying is we can't take the derivative at a point that does not exist. So for example, if we have a random jump continuity, so for example, let's say if we have a graph like this, we can't really take the derivative of that because first of all, the limit does not exist on both sides, therefore there's not going to be a limit at this particular point. So, and also, our limit definition and just our definition of derivatives in general is essentially saying, okay, what is the rate of change at this point? Well, if we're just kind of jumping back and forth, there's not really a way we can kind of figure out what the rate of change is when we have like a gap or something like that. So therefore it makes sense that we can't find the derivative of that either. So now it's also important to note that the converse of this is not true. So essentially, yes, we know that if that a function is differentiable as long as a function is continuous, but not all continuous functions are differentiable. So now let's go ahead and look into when a function is not going to be differentiable. All right, so now there's going to be really 3 instances where you can't take the derivative of a function, or at least not at certain points. So the first one is going to be at either what we can call either a corner or a kink on a graph. So essentially what they mean by that is if we have like a sudden sharp turn and like not even one where you can kind of like, for example, let's think about our absolute value function. Our absolute value function is going to go ahead and it just has it has a very defined corner right here, x equals 0. The thing is, we can't really take the derivative of this because we don't know. We don't have a tangent line at x equals 0 right here because, I mean, if you take the limit from one side, you get -1. Take the limit from the other side, you get +1. We do not have a tangent line at that point. Because of that, we can't figure out the rate of change. And because of that, we cannot find an exact derivative of that point. We can find a one-sided limit, but we cannot find an exact derivative at the point x equals 0. We could find it as x approaches 0 from either side, but not at that point exactly. We also cannot find if there's any discontinuity. This goes off of what I was saying earlier. Essentially, if you have a discontinuity, you can't measure a rate of change on something that doesn't exist. So therefore, any discontinuity would not be differentiable. And then 3 is if you have a vertical tangent line. Now, technically, the derivative of a vertical tangent line would be infinity. But, or you can just kind of think of it as the limit as x approaches your point A of the absolute value of your derivative is infinity. But technically, infinity doesn't, infinity is a concept, not a number, so you could, on paper, you could hypothetically say your derivative is infinity, but also it wouldn't really exist. You know, the whole weird infinity, it's kind of just once again falls in that whole infinity is a concept, not a number idea. Now, it's important to note that this usually is at certain points or intervals. So all of these, so maybe like in general, a function can still follow it, but like so this applies at any x equals a where one of the three, where one of the criteria occur. But going off of that, the rest of the function could be differentiable. So yeah, that's just something to take note of. So like for example, that absolute value function, you can still take your derivative at x equals 1, x equals 2, x equals -3. The only time you cannot take the derivative is at x equals 0. That is the one spot on that function where you cannot take the derivative. You cannot take the derivative if your interval includes x equals 0. But otherwise, it's fine. It's just those are the three things to watch out for when taking derivatives. So now that we have that, let's go over our notation real quick. So there's several different ways where we can go ahead and talk about, where we can go ahead and just mark down a derivative. So we've already taught you that you can mark a derivative as saying f prime of x. That means the derivative function. Well, f of x equals y. So therefore, you could also write this as y prime. Then you can write this in what is going to be called Leibniz form, which is going to be dy over dx. And essentially that's saying we are taking the derivative of our function y with respect to x. And going off of that, we can still rewrite that as saying df over dx. Once again, similar mindset, we can still say the derivative, we can still say d over dx of our function f of x. We can also mark this as using capital D f of x, or our derivative with respect to x of f of x. So yeah, all of these mean the exact same thing. So now let's go ahead and just think about, let's go and do a couple quick definitions that are pretty intuitive. Differentiation is just the process of taking a derivative. And then going off of that, we have what are called differential operators. And those are just symbols that signal to derive. And then our two differential operators are going to be the capital D and d over dx. So just essentially, if you see one of those two symbols in front of a function, that tells you derive that function. And also, one last thing that's important to note is that dy over dx is not a ratio. It's not really a ratio, just a way of, or at least for right now, it is not a ratio. Like, don't really treat it as a ratio. Just kind of think of that as saying, like, the derivative of y with respect to x. So now let's think about and move on a little bit further. We can actually, so we already know we can take a derivative of most functions. But you can also take the derivative of a derivative. That is very much so allowed. Now, this would be called a second derivative. And it would be marked as either f double prime of x or d squared y over dx squared. And essentially, all right, and real quick, actually, an application for second derivatives, because this will come up, an application for second derivatives is going to be finding the acceleration when given position versus time. And also, you can keep going as far as you want until it's physically impossible to take the derivative again. So you can find third, fourth, fifth, however far you want. As you can go as far as you want, as long as you can still take the derivative. Typically, your limit is going to be if you start getting where your function is f of x equals 0, that's about your limit. You can't go really past that. But you can just kind of keep going and going and going and going as long as you can physically keep taking that derivative. So let's go ahead and do one quick example, just doing multiple derivatives. So if we have a function f of x equals x squared plus 2x plus 1, we want to find f prime of x, f double prime of x, and you know what, why not? Let's even go for the third derivative. So let's go ahead. We kind of have to just kind of go in order here. So we're going to have to start off with just f prime of x. So our f prime of x is going to be equal to the limit as h approaches 0 of, all right, we've got a lot in here. We've got big parentheses, x plus h squared plus 2 times x plus h plus 1 minus x squared plus 2x plus 1 all over h. So of course, let's go ahead and start distributing and trying to simplify as much as we can down. So now we're at x squared plus 2xh plus h squared plus 2x plus 2h plus 1 minus x squared minus 2x minus 1 all over our h. So let's go ahead, cancel out any terms that we can. So we can cancel out the x squared. Let's see, we can cancel off the 2x and we can cancel off the 1. So now we are left with 2xh plus h squared plus 2h all over h. Well, we have a common h in here, so let's go ahead and get rid of that. H, 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 and h. This brings us to getting 2x plus h plus 2. Let's go ahead and plug that into our limit function. That's essentially going to get us 2x plus 0 plus 2, which is just 2x plus 2. Therefore, our f prime of x equals 2x plus 2. So now let's go ahead and we can go on and move even further. So now we know that our f prime of x is 2x plus 2. So now let's find our f double prime. So let's go ahead and do our second derivative is going to equal, just plugging this back in, so we're going to get the limit as h approaches 0 of, we're going to get 2 times x plus h plus 2 minus 2x plus 2 all over h. We can go ahead and expand that out to getting 2x plus 2h plus 2 minus 2x minus 2 over h. Let's go ahead and cancel out our common terms, which are going to be the 2x and the 2. So we are left with the limit as h approaches 0 of 2h over h. Those is cancel. So therefore, our final answer is just 2. Therefore, our second derivative is just 2. So now let's try moving on. Take the third one real quick. So now we're going to go ahead and have f prime of x, or f triple prime of x, equals the limit as h approaches 0. Well, there's no x in our function, so we just plug things straight in. So we can't plug in h anywhere, so we're just left with 2. Our f of our new function is just 2 as well, all over h. Well, we're just left with 0 over h. And this is one of those instances to where we're approaching 0, but we're not at 0. So therefore, we can actually still safely say that this is going to equal 0. And essentially, this is as far as we can move with our derivatives, because now we're just going to because if we could keep going on paper, but we'd still kind of get stuck in this loop of just getting all the way back to 0 every time. So that's what I mean when I say you can take the derivative as long as you want to, or like as long as you want to, but at a certain point, you're usually going to end up getting stuck at somewhere. Not always, but a lot of the more common times you'll get stuck somewhere. So now we are finally on to chapter 3, which is our derivative rules. So derivative rules are going to be very helpful because now we don't have to do the limit definition for absolutely everything. So, like for example, a lot of the sample problems I have done over the past couple weeks, I usually try not to do a power greater than 2 because when you have to start factoring out that many terms, it's a nightmare. So now our derivative rules, they will now let us be able to kind of move forward without having to do that. So now we're going to cover a few of the main rules today. We're going to cover rules involving polynomials, and we're going to touch on exponentials a little bit. So now let's go ahead and cover our very first derivative rule. So our very first rule, rule number 1, is going to be our constant multiplier rule. And as we move through these rules, they are going to seem very, very, very familiar because we have covered the a lot of these we've covered essentially doing limits, but I'm still going to kind of go over them. So our constant multiplier rule, similar with limits. So as our limit rule said, you can just kind of pull out a multiplier, put it in front of, take the limit, and then just multiply that. It's a similar thing. If you have, no, constant multipliers later. We'll do that in just a second. This is the constant rule. Misread my notes real quick. Constant rule. So this actually goes back to our last example. So once we got to a constant number, you saw we couldn't really plug it in anywhere into our equation. We would just keep getting 0 in the numerator, done, end of story, 0 is our derivative. Well, this is essentially just putting a name to that. Our constant rule states that if we take the derivative of any constant c, then that is just going to automatically go to 0. Yeah, like I said, we just did an example on that with that third derivative. So as you see, you just kind of get stuck in that loop. You can't go any further. We can just say it's 0, end of story. Now let's move on to the rule one of the rules you will probably use the most throughout all of calculus. It is one of the most fundamental rules, which is why they teach it so early. It is our power rule. So our power rule states that if we want to take the derivative of a power function that is x, that we can call x to the n, then that would equal n times x to the n minus 1. So now let's go ahead and talk about the power rule a little bit. So the thing we need to know is that this holds true for n is any real number. So yeah, this can go ahead and get us a long way. So just a quick example, just to show you how it works, is we're going to find the derivative of the function x cubed. So what we can do is we're going to go ahead and we're going to take this 3 and we're going to just push it right out down here in front. So we're going to end up getting with a 3. We're going to keep the x. And then now what we're going to do, now that we've pushed that down, we're just going to subtract 1 from that exponent. So 3 minus 1 is just going to be 2. Therefore, the derivative is just going to be 3x squared. And once again, this holds true with even fractions. So let's go ahead and do a quick one, another quick example. Let's go ahead and take the derivative of x to the 1/2. So the first thing we're going to do, once again, is just kind of pull that exponent and just kind of bring it down in front. So we're left with 1/2 times x. So now the next thing we're going to do is subtract 1 from our fraction. So 1/2 minus 1 is negative 1/2. That is actually perfectly okay. You can go ahead and even go down to negative numbers. As long as you get a real number in that exponent, you are fine. You can go ahead, this negative 1/2 up here is fine. So therefore, you would be getting d over dx of x to the 1/2 is equal to 1 over 2 x to the 1/2, or if you want to rewrite it, 1 over 2 square root of x. And yeah, once again, this allows us to kind of derive without having to do the limit definition every time. So for example, like if we had like a really, really, really long polynomial, that would involve a lot of like factoring things out, a lot of expansions, a lot of cancellations, that gets really, really tedious. That leaves a lot of room for mistakes. This is just essentially saying, okay, we have 2 quick steps, you can go. So now let's go ahead and think about what happens whenever we do start getting long polynomials. So we're going to have 5 rules whenever we're going to have, actually, we're going to cover 3 today because the last 2 are kind of wonky, because the other 2 are kind of wonky. So normally, when we had our limit rules, a lot of them are pretty intuitive. Some of these are the same, some of them are kind of different, but let's go ahead and go over these. So for right now, the next 3 rules you need to learn are the constant multiplier, Now the constant multiplier rule, it's similar to our constant multiplier limit rule. So essentially, if you're taking the derivative of a function that has a constant in front of it, what you can do is you can go ahead and just pull that constant out and just pull it in front and just say you're multiplying, you're just saying you're taking our constant times your final derivative. The next thing we're going to have is our sum rule. So now our sum rule, essentially if we have two functions, f of x and f of x, are differentiable, then we can say that if we have them combined in one, so if we have d over dx of f of x plus g of x, we can essentially break this down into two separate derivatives. We can now say that we have d over dx of f of x plus d over dx of g of x. After that, and then the last, or at least the last like polynomial rule we're going to cover today is going to be our difference rule. Our difference rule is pretty much the same as the sum rule. It has the same conditions. The only difference is instead of a plus sign, instead of adding, you're subtracting. So if you're subtracting two functions, you can split it up and subtract the derivatives of those two functions. So yeah, these are pretty similar to what rules we covered earlier in the semester. Now, our product and quotient rules, those are very different. So those we'll probably be covering, I believe, next week. But for now, these are your three main polynomial rules that you'll look at for right now. So actually, let's do a quick example. So now let's go ahead and we can do, now let's move on to some more fun examples. So now we want to find the derivative and why not, let's take the second derivative. Whenever we have our initial function is 2x to the 100 plus 3x squared plus 2x. So let's go ahead and start moving forward. So our f prime of x, what we can do is let's go ahead and take our derivatives. So we can go, let's go and apply our rules. So let's go ahead and say we're taking our derivative of 2x to the 100 plus our derivative of 3x squared plus our derivative of 2x. All right, so what we can do, let's go ahead and we can pull out these constants. So we get 2 times the derivative of x to the 100 plus 3 times the derivative of x squared plus 2 times the derivative of x. So now let's go ahead and we can move forward with our rules. So we have, pull out this 100 in front, subtract 1, which is going to get us 2 times 100 x to the 99 plus, let's see, we're going to pull this 2 out in front, subtract 1, which is going to get us 3 times 2x just to the first, so we can just say 2x. And over here, we have a little like 1 that's just not written down, so we're just going to pull that 1 out in front and subtract 1. So now that gives us plus 2 times 1x to the 0. So now let's go ahead and we can just combine these all real quick. So now this gives us 200 x to the 99th power plus 6x. And now we have 2 times 1 is just 1. And then x to the 0 is also just going to break down to just be 1. So we're just left with just our 2 right here. So now we can go ahead and know that this is our f prime of x. Now if we want to find our second derivative, we can still kind of keep going forward. So now that we've kind of shown how to break these down, you can kind of just sort of keep going. So now we have f double prime of x is going to equal, we can move this 99 out, multiply times 200, and subtract 1. And our 99 times 200 is going to equal 19,800 x to the 98th power. And then we have our 6x to the first. So we just pull that 1 out, which leaves us with just 6. Subtract 1, so we get x to the 0, which is just 1. So x to the 0 is just 1, so we're left with just that 6. And if we take the derivative of our constant 2, that's just going to be 0. So we can just say our final f double prime is going to be this 19,800 x to the 98th plus 6. So now there's going to be one more thing that we need to cover real quick. So now we've touched on a lot of polynomials. We've touched on our basic derivative rules. Now we need to go ahead and think about our exponential functions. So now let's think about our exponential functions in terms of our limit definition. So let's say we have a general exponential function where f of x equals some constant b to the x power. When we plug that into our limit definition, we are left with getting f prime of x equals b to the x times our limit as h approaches 0 of b to the h minus 1 over h. So let's go ahead and think about this. Let's go ahead and think about this a little bit further. So if we just have our b, so if we're trying to find f prime of 0 of b to the x, we are actually going to end up with just getting b to the h minus 1 all over h, because we'd be getting x plus h in the numerator, but that would end up kind of getting eliminated. Or well, actually, it would be 0 plus h. 0 plus h in the numerator for the exponent, which is just going to break down to h. And then any number to the 0 power is just 1. So that's why we're getting this b to the h minus 1 over h. So now that we have this, we can essentially say that there is a relationship between f prime of 0 and f of x. So essentially what we can say is that our rate of change, or our derivative, of our exponential function b of x is proportional to the function itself. So what it means is that essentially we have this f prime of x. What they're saying is, like, if we think about it, we can say that f prime of x equals f prime of 0 times b to the x. So essentially that's what they mean, is that we have our function and then we have our derivative, and that's just saying that as our derivative is going to go ahead, is going to be affected by a similar scale based on our function. Or in other words, our slope is proportional to our height. So now let's think about now that brings us to the discussion of what the number e actually is. So now let's go ahead, and so now that we have that out of the way, essentially for any value for b that we plug in, we can get different values for that slope, or for that proportion. But it's only going to be one value to where our f prime of 0 to where f prime of 0 of b to the x equals 1. There's only going to be one value, is when b equals e. So essentially the definition of e is it is the number such that the limit as h approaches 0 of e to the h minus 1 over h equals 1. So, or in other words, like I said, our derivative at 0 of our exponential function is going to equal 1. So what they're saying is that e to the x is the only exponential function use tangent line. At x equals 0, or at x equals 0, has a slope equal to 1. And because of this, e and its function e to the x ends up getting a lot of really interesting special properties. So, and one interesting thing because of this is that when you take the derivative of our e to the x function, you are literally just going to get e to the x spit straight back out at you. Now, if you wanted a more in-depth proof of this, I would definitely recommend checking out the textbook or asking a prof, because I know this was just a super Cliff Notes version of the proof. But if you're interested in learning the math behind it, I would definitely go seek out those sources. But now we have this, our last derivative for the day. So I want to just do, before we leave, I just want to do one last sample problem, just to kind of go ahead and just work on what combine everything we've learned so far today. So now what I want us to do is I want us to find the third derivative of our function x to the 5th plus 2x to the 4.5 plus 3x squared plus x to the negative 1 plus e to the x. All right, so let's start breaking this down little by little. So first, let's go ahead and figure out and just take our derivatives one step at a time. So let's go ahead and find our first derivative. So we're wanting to get to our third derivative, but right now we're still at our first, we need to go ahead and go through our first. So let's go ahead and break down each of these and find the first derivative. So we have d over dx of x to the 5th plus d over dx of 2x to the 4.5 plus d over dx of 3x squared plus d over dx of x to the negative 1 plus d over dx of e to the x. So let's move forward a little bit. So rule number 1, we just have our power rule. So we can just pull out that 5, subtract 1, which is going to give us 5x to the 4th. All right. Now we have our, once again, we have our power rule and our constant multiplier rule. So let's pull this 4.5 out in front and then subtract 1. So now we get 4.5 times 2 is 9. X to the 4.5 minus 1 is 3.5. Plus, we can go ahead, pull this 2 out in front to where we get 6. X, 2 minus 1 is just 1, so we can leave that. Plus We can pull this -1 out in front, so where we get negative x, -1 minus 1 would just be -2. Plus, derivative of e to the x is just e to the x. So now we have our first derivative. So now we need to go ahead and move on to get now our second derivative. So once again, let's just go ahead and keep pressing forward. So where we get, once again, we just have our power rule right here. So now we have our power rule, so we can pull this 4 out, and pull this 4 down, subtract 1. So 4 times 5 is 20. X, 4 minus 1, which is 3, plus, we can pull that 3.5 out in front. So we get 3.5 times 9, which is 31.5 x. So 3.5 minus 1, which is 2.5, plus 6x to the 6x to the first. So pull that 1 down, which is just 6. And then 1 minus 1 is 0, which is equal to 1, so we can just leave that 6. Plus, we have our -2 times our -1, which is just 2x. -2 minus 1 is -3. And then, once again, the x just stays put. So now we need to go ahead and move do this one more time to get us down to our third derivative. So once again, we can go ahead and just pull this 3 out in front. 3 times 20 is 60. X, 3 minus 1 is 2, plus 31.5 times 2.5, which is going to be 78.75 x, and 2.5 minus 1 is 1.5, plus, well, we just get, well, our derivative of 6 is a constant, so that's just going to go out to 0, so we don't even have to write it down. We can just move forward. So now we get -3 times 2, which is -6, x to the -3 minus 1, which is -4, plus our e to the x. Actually, I'll write a little +0 just so we know where it came from. So now we can clean this up and officially say our third derivative of our function is equal to 60x squared plus 78.75 x to the 1.5 minus 6x to the -4, or 6 over x to the 4 plus e to the x. All right, that will conclude the end of our session. So good luck to everyone and have a wonderful day.